Good afternoon, I'm Shiyi, a master's degree student from Chang'an University. The direction of my study is industrial vision based on deep learning.
It is my honor to present our work. The topic is radiographic inspection of submerged arc welding using semantic segmentation. This report will introduce a project from 4 parts. Submerged arc welding is employed in an extremely wide range of industry domains, including construction, aerospace, cargo, electricals, and energy. Before that, many scholars have developed a variety of methods to detect weld defects. These methods mainly focus on the detection of welding defects, while we try to use a one-stage semantic segmentation module to yield pixel-level inference of weld area and defects simultaneously. In this section, I will introduce our experiment from 4 parts. Digital radiography is one of the most reliable techniques for welding inspections, and there are many advantages of digital radiography, such as instant imaging, high sensitivity, and so on. The data acquisition process is shown in the figure. The image on the left was taken at an oil pipeline factory where we conducted the experiment. Some DR images we collected are shown in the figure. Common defects mainly include porosity and discontinuity. In this work, we employed a fast semantic segmentation network, which is called FastSCNN for our mission. An illustration of the framework is shown above. Schematic comparison of FastSCNN with encoder-decoder and two-branch architectures is shown above. FastSCNN encodes spatial detail and initial layers of global context in learning to downsample modules simultaneously. This can reduce the operation cost and improve the speed of module. Our setting for model training is shown above. This model can almost realize real-time inspection and support multiple input image resolutions. In order to make the results more accurate, we added logic judgment before outputting the results to judge whether the defects marked by the model are located on the weld. Some prediction results of the model are shown in the figure. The results suggest that our method yields quality pixel-level inferences. From the generated pseudo-color semantic mask, we could obtain more information of area, size, and position of welds as well as defects. As shown in the table, our methods gained very high accuracy and efficiency, which enables real-time inspection. Finally, our method basically achieves the preset effect. Our future work will focus on the challenging task of improving the segmentation precision on tiny defects. That's all. Thanks for your attention.